people on 5, and then we like to be 8 people.
Right. It's the fourth valence, right?
Right. So, how did you figure that out?
First I did the Lewis.
So you determined valence electrons
Yes.
by doing what?
Well, first I determined how many electrons there were. It was 14.
Right. So silicon, yeah.
What I did was I went through the what's called
Electron configuration.
yes. So 2 pieces.
Yeah.
And that's 10. So everything else on the outside of that were the 4 electrons that are. That's what's over here, Mike. On the outside of it. And the way I read it was the symbol is faced with the 2 electrons that are catons, cations. And then there were 2 others, and they were anions, right?
Cation is an ion that has a positive charge. An anion is an atom that has a negative charge.
I know that if you did 4, it would be 2 there to start with, then 1, and then 1. And that I remember reading it.
I thought they were opposite of each other.
Yeah, actually, so you got the four is correct. That's perfectly correct. When you figure out 4, you want to keep them separated until you have to start pairing them. So I personally go left, right, up, down. It doesn't really matter what order you go in. But number 4 would be
Is it?
here.
Thought they were paired up first.
So, fortunately, you were in class. You didn't see a shortcut. What you did is completely correct. Completely correct. Okay. Yeah. How would you do that more quickly?
I just went from the noble gases, went backwards.
And when you did that,
Yeah,
what did you actually do?
It was 4 away from the noble gases.
Okay, so you saw then, if it's 4 away from the noble gas, how do you then get 4?
It wants 4 more to be a noble gas.
It wants 4 more.
4 more electrons.
Right.
So that has a complete shell.
If it wants 4 more to get to 8, that means it has 4. Is there another way someone else looks at it? 'Cause
I just counted
from the
left to right.
Yeah, I come from the left. So I go 1, 2, 3, 4. But however you get from point A to point C, whether you go through point B or not, all that matters is that you got to point C. Whatever works for you. If it helps you to do this, great. If you want to start on the right and go left, fine. Go left to right, fine. Okay? So then you figure out how many valence electrons and you put that many dots around here. A noble gas, what will the dots look like for a noble gas?
2 on every side.
4 pairs, 2 on every side. Is literally 8 of them. Thank you, Luca. What else? Yeah.
I had trouble with number 32 on the chapter 5 homework.
Number 3.
Let me bring that up.
I felt really, really, really stupid.
I can give you the information we need.
Like,
We'll get it up to that way everyone can look at it. People look at it.
but the 3 numbers, I started to understand it. For a second, I'm like, oh, like, it just felt really dumb.
Yeah, like 32 and 23.
Can you even read? Is it too small?
23.
No, it's 17 protons. And you're gonna have 17 electrons. So you're gonna have 18 electrons.
23?
Okay, does anyone know how to do 32? Yeah, Matt. I got quite a few emails about this last semester too, but I still like the question because it makes you think.
I got really stupid, actually, when I went back and read it again after.
This is the one that you said don't understand.
Yeah.
And I worked on it.
Yeah, so did I.
How many times? I don't know. It has been on the internet for over 7 years, it's causing problems.
Okay, so I want you to find Q, and it says you have Q60 and Q63. And then it says that the average AMU is 61.5, which is halfway between 60 and 63. So you would have 50% on this side and 50% on this side.
That's why I said you could probably do it in your head.
Don't overthink it.
I had like a formula written down, you wrote that.
If that number was anything other than 61.5, it immediately gets magnitudes more difficult.
Yeah, but I was doing like X and X minus.
Oh, yeah. Yeah.
Okay, cool. That's good.
I think last semester, a student emailed me, and I started doing it that way. And I'm thinking, wow, this is so hard. Why is this even in this book? And then it dawned on me. It said, oh, okay. And of course, that was after I actually solved this the other way with the algebra and the substituting variables and everything. And it comes up with 50-50.
Yeah, I was wondering how I was
When I finished doing the algebra on it, I went, oh crap.
Are we ever gonna have one that's gonna, we have to use the algebra in?
No. I like it because it makes you think, right? It's just like that. If this was closer to 60, which one is there more of? 60. If it's closer to the 63, there's more of the 63, right? And so in this case, you can see it's in the middle, but the middle has a specific number to it that you can say it is 50%. Right? So what else? Gotta be more.
Literally only 23 and 32 are two that I was stuck on. But I ended up figuring out 23 because I found out that it has to equal up to 100%.
Yeah.
So-
Yeah. Get emails on that one too. The ones where it gives you the abundances, but it only gives you abundance of one of them.
Oh.
One of the two, so have to equal 100. Is that really it?
I'm just glad my 10-year-old's smart. Well, I guess he's the one.
Yeah. So you got 23 now.
Yeah,
Can
I
you
just have to
explain
finish doing the math on
that
it.
chart, the ionization energy thing again?
Let me bring it up. Is there anyone that feels comfortable explaining it beyond what's written on the slide? No? Is that because you don't remember this at all? So you don't remember the pattern? Or you just took
So you
the
take that.
student route and memorized the pattern and said, who cares why?
Yeah, that one.
That one? So, what has the highest ionization? Which element? Helium. Okay. It's easier, in my mind, it's easier to remember and figure out and explain why it gets higher as you go from left to right. Okay. The ones that are on the left, what charge do they like to form? The elements that are on the left-hand side of the periodic table, what charge ions do they form? Positive. If they're forming positive ions, what's happening to their electrons? They're losing them, right? Ionization energy is how much energy it takes to pluck off one electron, okay? The elements in the first column here, what's the technical word for a column? Group.
Oh.
Group. What's the rows? Periods. Okay. So the elements in the first group only have one valence electron. they want to lose that electron, right? So if they want to lose it, it's not going to take much energy to steal it away from them, right? They basically give it to you. Think of this as how much money it costs to bribe someone into giving it. Okay? Money is energy, and they're giving up an electron. Okay? Let's come to the other end. Say you're fluorine. What charge do you form? Negative. -1. Because remember, everybody wants to get to be a noble gas. If you're one shy of being a noble gas, you don't want to give one up, because then you're too short, right? So you're going to have to bribe me a whole bunch of money to get me to give you one of my electrons, right? Because I want it, okay? It's not like, I don't know. I'm not even going to come up with an analogy. It's just selling something on eBay. You can come up with your own.
Like playing Monopoly.
Yeah. So if you have, what's one of the purple ones? Baltic Avenue, maybe? Anyway, fluorine is Park Place and Boardwalk, right? If you got that, you're gonna have to. I'm gonna have to pay you a lot of money to sell it to me, right? Especially if I already have Boardwalk and you have Park Place, and you know you're basically giving me the game by selling me the other one. Okay. So these want to lose an electron, these don't. So you have to give a whole lot more energy to these to make them lose one. Okay. To me, that makes a little more sense. Okay. Going down, it gets easier. Okay. Say we have our nucleus. Okay. And here we're going to use that outdated Bohr model. Okay. With the nucleus and the rings. Okay. As you go down the periodic table, as the period number gets up, you're moving further and further out. Okay, you're going to orbitals that are further away. Okay. Say we have an electron that's here, so it's very close. Okay. If it's very close, that means it's towards the top, right? But say we have another one that's further away. That's more towards the bottom. Okay? What is holding these electrons in orbit? The protons. And what about the protons? Wait, it's actually the charge. Okay. It's
Charge between the proton and the...
right. So there is gravity attraction between them, but the charge attraction is a whole lot stronger. Okay. So the electron has a negative. The electron has a negative. And the nucleus overall has a big positive charge, okay? And if you've taken physics, the closer two opposite charges are, the stronger the attraction. You know this with magnets, right? You put two magnets close together, there's a strong attraction. You pull them apart, it's basically no attraction at all. So these have a very strong attraction to the nucleus. This one is a little weaker. Okay? So if you're going to pluck this electron off, it's easier. There's less attraction pulling it to the nucleus, which is why as you go down, it gets easier to pluck them off because you get further and further away. So you can remember those two concepts, or you can remember helium as the highest. Up to you. It works as long as you remember it. But if you know a concept, you can figure it out on an exam or a quiz. What else?
Why don't we just go over the answers, then we can ask why we were wrong on certain things, and then figure out why?
We cannot go through the answers on all of them.
Okay. That's worth a shot.
Worth a shot.
And you said not to do number 9? Is that one you're not looking at on here?
What else?
This is a wing stop configuration one.
There. Number 9A was wing stop.
Right.
B and C, you have to do.
Oh.
Yeah.
Can you take a look at two on actual printed homework?
I don't think I pulled that up. What was the question?
It was, they gave you two elements, the masses and the abundances of the isotopes, and you had to identify that one.
Dang.
But my math, I'm not right, it's maybe math that I recognize.
So you've got 38. 38.012.
Ooh, can I take a whack at this one?
Yeah, well, I'll get it written up here and then you can write your questions.
Huh? What'd you say?
Whack it away.
Whack it away.
Thank you. Go for it.
No, I write all these out and then I round it to the 4. Sig figs.
So what element is that? Which is, I think that's what the question was asked.
Yeah.
So that is argon, 39.948.
Oh yeah, I did.
That's what I had, for some reason I thought I was wrong, I don't know. I have a star next to it.
You don't have to round those two, do you?
Well, yeah, it was a multiple choice, so the multiple choice answer was argon, so sig figs really don't matter. What else?
To chapter 10, number 3.
Let me see your notes there, how it's all. Mine doesn't.
Chapter 10, number 3?
Yeah, lost my
The ones on this side are the ones that are with the homework, and then the other ones are just whatever.
I count
These are
on,
the ones we need for the homework?
Yeah, that's the ones that pulled out. that-
Yes,
Do you
that
separate your
relate to the
classes by
homework.
folders? Do you separate them by folders?
So who wants to
I
do
want to.
number 3A? Electron configuration for scandium.
Do it.
3A.
Yeah.
Just write it out and explain it. Okay.
Explain.
We'll just try to explain your thought process.
Okay.
There you go.
You're gonna explain that thought process?
No. You were going to
I
explain the
thought
thought
you were
process.
gonna explain it.
3A.
Okay, so.
On the chapter 10.
Oh,
Can you talk about
oh.
So scandium is here.
Okay.
So there's, this
So-
is the number we're looking at right here.
Okay,
So since, you know, each row, and the first row, the first two columns are gonna be your S, then you have your D, and then your P. So, 1S, we're gonna go all the way over to 1S, then you have 2S, which is 2. And then we're gonna go down to the second row, which is P's, and that can hold up to 6. And then we're gonna drop down to the third, is it family, group? Yeah.
So the
Third
rows or
row.
periods?
Third period. Now, when you get to D, you have to subtract one, so although this one here says 4, when you get to D, it's gonna be 3D1.
That's what I got.
That's what I got.
let's not give you that all.
So, this is correct.
Okay.
Okay. The way I do it, start in the top left, go left to right, top to bottom. Write down the orbitals as you come across them. Okay? So top left is hydrogen. Okay? The first orbital is always 1s. Okay? Helium and hydrogen fill that 1s. Okay? We are past the 1s. So I would write 1s2. S's hold 2. We know it's full because we're well past that in the periodic table. Okay? If you don't know that, you can just write out the orbitals, count how many electrons you have, and then come back and fill them. Okay? So I would write 1s, 2, and now we're here, which is 2s. It's full, so it's 2s2. Come here, that's 2p. It's full, so that's 2p6. Here, 3s2. 3p6, 4s2, and then like she said, that's a d1, but it's 3. The d's are set back one number.
Okay, do that again.
So you have 1s2,
Okay,
2s2,
uh-huh,
2p6, 3s2, 3p6, 4s2, 3d1.
okay. Gotcha. Where, the top number is what again?
That,
Uh-huh,
so this doesn't have to be here.
okay,
These numbers aren't required to be here.
okay.
As long as you give me the element name and then that. She wrote this because this tells her how many electrons she needs.
Mhm.
Rather than looking up there, she has it here. The top number, what is this top number? Neutrons plus protons, which is called what?
Atomic mass.
You're very close. The mass number.
Mass.
Okay. Which is essentially the same as the atomic mass, but this, in this situation, has a different name called the mass number. So let's do, what's B?
B
Rubidium.
is rubidium.
Rubidium. Who wants to do rubidium? Where is rubidium? Rubidium, right, thank you. Wow. I would suggest, if you want to do it,
Noble gas?
I was going to say, if you want to do noble gas, you can do noble gas.
Could we have done it with that?
No, because it specifically
Okay,
says,
I did.
yeah, because
Because of that.
it says right to complete.
It's just so many.
It's just so many. Why don't you do both? Yep. Yeah, that's the easy one.
Alright.
Okay, so what did you
Easy
get
way.
KR from?
Oh, well, she's going to do the whole one
Okay.
now, and then we'll compare them.
And this number.
3B.
No.
Brain, it was, I mean, I was here.
If you want to do a shorter way, you want to do the noble gas.
So,
Put the homework.
okay. Good job. So, one thing that's missing RB.
Oh, yeah, A-hole.
Okay, so this question did specifically ask, write the complete electronic configuration, which is this, which is what we just did for Scandium, but longer, okay? This is a noble gas notation, so that you don't have to write all this. All that really matters is what's at the end. So we find our element that we're starting at, which is right here, and we go backwards until we hit a noble gas. So rubidium goes back to krypton, okay? So we just write krypton, meaning we're starting at krypton. And then we just write what is after krypton, which is 5s1.
Do we have to have both formats?
No, because we'll look at the question. The question will tell you what to do. It says write the complete electron
So
configuration.
that's the long one,
That's the long one.
yeah.
Yep. So if you look at the written homework, I think one of them I said use the noble gas notation to write the electron configuration. In the written homework, the one with the problem I wrote,
Okay,
I think I said use noble gas notation to write the electron configuration.
okay.
Okay. And then the other one specifically said write an orbital diagram, which is the one with the boxes. And you can never, ever use noble gas notation with the boxes. Okay? You can only use noble gas notation with the electron configuration.
I know I came in late, so I already did this question and I'll ask you later, but could you do number 32 in chapter 5? Please, I mean, it is, my brain is just,
What was it?
I feel like more than 16.
Was it,
Yeah.
was it 40 and 43 or 60 and 43?
60 and 63.
60 and 63.
Hold on.
So you have, what was,
Yeah,
what was the element symbol that it had?
Q.
Yeah,
Q?
how you do that?
Q60
Okay.
and Q63 and the
61.5.
61.5 is the average atomic mass.
Yeah.
Okay? So, you're 60 and 63. Where in that does 61.5 fall?
In the middle. Somewhere.
Right in the middle, right? So if you took the average of that and that, what number would you get? You get 61.5. So if the average is right in between them, what is the breakdown of the percentages for the left and the right?
50-50. No.
Yeah.
Yeah?
Right?
Yeah. So because it's right in the middle,
Right in
know
the
that it's
middle. 50-50.
We all did the algebra around the East Coast.
Don't, you missed the story of me explaining how last semester I did it the hard way and then got the answer and realized it was 50-50. Because I didn't notice it either. So
Wow.
if you make that just
Don't overthink it.
61.49,
Because I sure overanalyzed.
it's all of a sudden a whole lot harder.
Okay. Thank you.
You're welcome. Okay, let's move on. So, last week we learned about atoms. Okay. Today we're going to start combining those atoms. And remember when we talked about combining atoms of different molecules, it's called, of different elements, those are called compounds, right? So today we're going to be talking about chemical compounds. Yeah. You can just turn in a break.
So did we fill that for the YouTube part?
Yes.
No, we did?
Yes. I think we missed like the first 30 seconds, but.
Okay.
Did anyone watch that last week?
Yeah. I watched.
Could you read the board better this time?
Yeah, all I had to do was pull up the PowerPoint, but the board stuff was all fine.
Okay, because I know the first time we couldn't really read it up there.
It was good from what it was last time.
Do you have a question?
Yes, is one of our labs gonna be where we can like create something from mixing two chemicals?
Are you talking like an actual chemical reaction or with models?
No, actually chemical reaction.
Yes, yes,
Cool.
yes. Okay. So just like with everything, especially that first week, you can have subclassifications, right? You are subclassified out of your mind that first week, right? Two types of compounds, ionic and molecular. Sodium chloride here is an ionic compound, okay? When you look at that, what you see is you see sodium ions and chloride ions, right? There's ions in there. This is a molecular compound, okay? This is an organic compound. We're not going to be doing organic chemistry. This is how you draw organic compounds. All the corners are carbons, okay? All the lines are bonds. So it's a single bond, it's a double bond, okay? You don't have to worry about this. We are going to be doing molecular compounds that are not organic though. But in every molecular compound, it's not made up of ions, okay? And there are different types of bonds that go into this that we'll see. But ionic compounds are made up of ions, molecular compounds are not. Okay. Ionic compounds have a metal cation and a non-metal anion. Are cations positive or negative charge? Positive. So anions are negative, okay? Here is your key to determining whether something is ionic or molecular. If there is a metal in it, it's ionic, okay? Especially in this class. If there is a metal in it, it's ionic, okay? So find your stair step, eliminate the metalloids, which we won't really be dealing with at all. If to the left of that stair step, it's ionic, okay? So sodium chloride, we said is ionic. There's sodium, that's a metal. Boom, it's ionic. Okay?
Doesn't matter what it's mixed with. as long
Doesn't
as
matter what it's
there's
mixed
a metal
with. Doesn't matter what it's mixed with. If it has one metal in it, the whole thing is ionic. Okay? So if you have something that's, say, manganese nitride, manganese and nitride, you don't know what that is, but it's ionic, right? It has a metal in it. You don't need no more than that just to classify it. When you make an ionic compound, the cations, the positive ions, and the negative anions are going to come together in a ratio that they cancel each other out with their charges. Okay? What's the charge on a sodium ion? Sodium's there. +1. What's the charge on a chloride ion? -1. +1, -1, 0. Right? They cancel each other out. Okay. In ionic compound, all those ions, like we saw on the last slide, are put together in a crystal lattice. They just basically stack in a pattern where the positives and the negatives cancel each other out. So if you have a grain of salt, what's in there are sodium and chloride ions just arranged in that crystal lattice. Ionic compounds are called salts. We call sodium chloride salt. In chemistry, it is just an example of a salt. Any ionic compound is called a salt. We won't really use that term in here because it's very confusing, because when you hear salt, you think sodium chloride. Okay. So we're going to be dealing with ionic compounds, not salts. Molecular compounds have two or more elements, but there's no nonmetal. Sorry, there's no metal, which means you have at least two nonmetals bound together. Okay. CO2, carbon and oxygen, two nonmetals. O2, oxygen. Oxygen is one of those diatomic ones. So you have oxygen bound to oxygen. Oxygen is not a metal, so it's molecular. Okay? Because they're not ions, there is no charge anywhere. Yeah.
Now, when you say two or more different non-metals, do you mean by atom or by density?
Either one of them. Here you have two different elements. Here you have two atoms, neither one of them, they are both non-metals. Right?
So, by atom.
Yes. Yeah, if that's how you see it. Bottom line is, there is no metal. And so by default, process of elimination, it's molecular. Okay. These exist as molecules. We'll talk about the ionic ones. They're not actually molecules. Sodium chloride is not a sodium chloride molecule. It's a sodium ion next to a chlorine ion. They have opposite charges that just kind of stay next to each other. Okay? It's not a molecule. Molecular compounds actually form molecules, which is why they're called molecular. These are properties of ionic molecular compounds. Don't go memorizing all of them. Most important thing is I would focus on melting points. Okay, ionic compounds have high melting points. You've probably never even considered melting sodium chloride, right? But if you've ever made candy, you've melted sugar. Sugar is a molecular compound, okay? Oxygen, we saw, was a molecular compound. At room temperature, oxygen is a gas, which means it's well beyond melting, right? And then also, ionic compounds are what we call electrolytes. And we'll come back to this later, I think. Electrolyte is something that when you dissolve it in water, it will conduct electricity. Okay? Molecular compounds are either very weak electrolytes or non-electrolytes when you dissolve in water. An aqueous solution means dissolved in water. If you put sodium chloride in water, it's going to conduct electricity. Pure water by itself actually does not conduct electricity. But if you get tap water, it's going to conduct electricity because there are ions in it. Which is why they always say don't put a toaster on the tub next to you, right? Or don't dry your hair in the tub. There's going to be ions in that water, and so you're going to electrocute yourself. Okay? But water that is full of molecular compounds will not conduct electricity. So pure sugar water won't conduct electricity. And this is one of the labs we're going to do. So we'll measure a whole bunch of solutions to see if they conduct electricity. I think we did that. CCl4. Ionic or molecular?
Molecular.
Why?
There's no metal.
No metal. Okay. Calcium fluoride. Ionic. Why?
Metal.
Metal. SF6. Molecular, there's no metal. Oh, that one?
Metal. Metallic.
Ionic. Copper is a metal. H2O. Molecular. Okay. H2O is a complicated one. That is not something you would be asked on a quiz or an exam, because depending on how you want to argue it, you could argue H2O either way. And as you go through the semester, you'll see that. Okay, so we're not going to even spend time on it. Okay, but to us, H2O is molecular. Based on what we just talked about, the properties of water, how could you argue that water is a molecular compound, not ionic? Not ionic.
Like solid or brittle.
What about the electricity? What did I say about pure water?
It doesn't.
It doesn't. Ionic compounds conduct electricity. So if water was truly ionic, it would conduct electricity. Which has the highest melting point? That one, top one, or the bottom one?
Top one.
Why?
Cesium is metal.
Cesium is a metal, which makes that one ionic, and we said that ionic compounds have the higher melting point. There's the same exact trend with the boiling point. So which one has the highest boiling point? CO2 or CaF2? CaF2. Calcium is a metal, that makes it ionic, it has the highest boiling point. Okay. I didn't point out density. Let's go back. Ionic compounds have high density, molecular compounds have low density. So which one has the highest density? K2O or SO2? I heard both. Why K2O?
It's a metal and the metal.
Yeah. Potassium is a metal, which makes it ionic. If we were to go back, it said ionic compounds have high densities. Okay. So I talked about things being electrolytes. For something to be an electrolyte, when you dissolve it in water, it has to break apart into ions. Okay? When you dissolve sodium chloride in water, what you actually get are sodium ions flying around and chloride ions floating around. Okay? At that point, they don't even know the other one exists. They're completely independent of each other. Okay? Sodium ions have a positive charge, chloride ions have a negative charge. For something to conduct electricity, you have to have charges that can flow. Okay? So with our electricity, in our wires, electrons can flow. Okay? Electrons have charge. In copper wiring, electrons can flow from one end of the wire to the next, carrying that charge, that electricity. Okay? In ionic solution, so say sodium chloride dissolved in water, the positive ions can actually move from one side to the other, and the negative ions can move from one side to the other, which carries the electricity. Okay? If you put sugar in water, it's a molecular compound, it actually doesn't break apart. It stays sugar. Sugar has no charge. So it has no charge to move around, so you can't transfer any sort of electrical charge. Okay. Here, this is CH3OH, which is methanol. Okay? We put methanol in water. It goes from methanol liquid, remember our little state symbols, methanol liquid to methanol aqueous. Nothing changes except the state symbol. Okay? It's methanol, it's methanol. Oxygen gas dissolved in water becomes aqueous oxygen. Okay? If we go back to sodium chloride, here we have sodium chloride solid is breaking apart into the sodium ion, aqueous, and the aqueous chloride ion. Okay? They break apart. And there will be more examples of this. There are monatomic ions and there are polyatomic ions. At this point, all we've really talked about are monoatomic ions. So when I say, what is the charge on a sodium ion? A sodium ion is monoatomic. Okay? There's one atom. It's a sodium ion. Okay? It's an ion of a single atom, and it has gained or lost electrons to have a full valence shell. It has 8 valence electrons. So a chlorine ion is a monatomic ion. Okay? The transition metals, where I think that was before class, we were talking about them, they can actually form different charges. Okay? Almost all of them will form +2, just like the second group, but there are some exceptions. Okay? We'll come back to that again also. So I've been saying these ion names, and some of you may be been sitting there thinking he's talking and saying these, but he hasn't gone over them yet. So here are some ions and some names. look through there, and if you see if you see any patterns.
Anything with a negative ion is like oxide, nitride, you change the name.
Right. So if you have a negative charge, you take the first part of the element and you add "ide" onto it. Oxygen becomes oxide. Nitrogen becomes nitride. Chlorine becomes chloride. Fluorine becomes fluoride. Yeah.
Is it just a coincidence that the other one's in IUM, or is that true for all elements?
Coincidence. A lot of them end in IUM. Let's say manganese or tungsten,
Yeah, okay.
platinum. Some of them don't, a lot of them do. And if you do look, most of the IUMs are on the left, they're metals. If you have a positive charge, you don't change anything. You just say the element and then say ion. So you have a sodium ion and you have a chloride ion. Okay? These are a lot of the monatomic ions you're going to be dealing with the most. This is not a thing to memorize, because remember, from here on out you have a periodic table. So if I told you what is the charge on a calcium ion, you should be able to tell me. You don't have to memorize that. Right? What is it? +2, or 2+, however you want to say it. Okay? So remember, these form +1, +2, -1, -2, -3. Transitions metals, this says typically form ions with variable charges. To me, they generally form +2s, and the ones that do form variable charges are the exceptions. Okay, and we'll still have to come back to that. Those are monatomic ions. There are polyatomic ions. A polyatomic ion is a group of ions that overall have a charge, okay? And then they're going to act just like a monatomic ion. As a group, they're going to act just like a monatomic ion. So that is sulfide, that's monatomic, okay? Here is sulfite, SO3, a sulfur and 3 oxygens with a -2 charge, okay? And there is sulfate, that's SO4 with a -2 charge. So you can see the difference between a monatomic ion and a polyatomic ion. Okay? A polyatomic ion that has at least 1 oxygen in it is also called an oxoanion. Okay? That's not a term you're going to come across very often. Okay? But it is in the learning objectives for this course, so here it is. Names of the polyatomic ions, for the most part, you just have to memorize. There are some patterns. Okay? Look at these and see if you see a pattern.
Ion.
Yeah. 3s have 8 and the 2s have 8.
You're on the right path. You're very, very, very close. That's a 4, that has an 8.
Oh. Yeah.
You're you're so close. You're so close.
Above 2 is 8.
You're so close. Because here's a 3, that's an 8. Well, let's look at each pair in isolation. Okay. Here is NO3, NO2, nitrate, nitrite. Okay. Which one has more oxygens? Nitrate. Let's look at these. SO4, SO3. Which one has more oxygens? Sulfate.
So whichever one has the higher.
Yeah. Yep. So for each one, there's a starting point. Okay? And that is the 8. With the nitrogen with oxygen, NO3 is our starting point. That is our 8. If we take one off, we become ite. Okay? Sulfate, SO4 is our starting point. If we take one off, we become SO3, and we go from 8 to ite. And then chlorate, 3 is our starting point, 3 is our 8, so 2 is our ite.
What would dictate the starting?
Yeah.
What,
A lot of it is, most of it is how common they are. It could have been the first one to be discovered. You definitely see nitrate, sulfate, and chlorate a whole lot more than you see nitrite, sulfite, and chloride in a lab. They're just a lot more abundant. Okay. These are a big list of polyatomic ions. Don't freak out and think you have to memorize all of them at this moment. Okay? Okay. I'm blocking some of them out. Those you don't have to worry about at all. Okay? There is a file on Canvas under the course files module that says polyatomic ions and oxoacids you need to memorize. Okay? I believe it is basically this minus a few. Okay? But that is your definitive guide to which ones you have to memorize. Okay? If it's not on there, I cannot specifically ask you on a quiz or an exam, what is this? Okay? Give you a name. I can't tell you which one of these ones, oxalate. Okay, I know oxalate is not on that list. On a quiz, I can't say, what is the formula for oxalate ion? Okay? But something I know is on there is nitrate. Nitrate is very, very common. So it is more than fair game to say, what is the charge on the nitrate ion? Or to say, what is the name of the NO3 minus ion? Okay, so look at that sheet.
So you gotta memorize the composition and the name.
Yes. It's just like memorizing the symbols and the names. You need to be able to go between the symbols and the names. Okay. This is calcium carbonate. All we did is we combined the word calcium with the polyatomic ion name. Okay? With monatomic ions, we have to take the element and then change it to an ide, right? Chlorine becomes chloride. That already is carbonate. CO3, 2 minus, is carbonate. So we just say calcium carbonate. That's it. Okay? Anyone know what calcium carbonate is? Yeah.
it's the stuff that makes up seashells.
Seashells? And then what else what do we actually make from seashells sometimes?
Necklaces.
Necklaces. Think this classroom in the 30s or 40s or 1800s or something.
Chalkboard?
Chalk.
Oh,
Chalk is calcium carbonate. Okay? Tums, I think we had a problem on one of the homeworks, or the quiz about Tums or Mylanta or something. Right? So that is calcium carbonate. It's basically seashells. Okay. This is sodium bicarbonate. HCO3 minus is bicarbonate. So it's just sodium bicarbonate. Just read it off. Sodium cyanide.
Why aren't the pluses behind it?
We'll see.
Okay.
We'll see. This is potassium nitrate. NO3 is nitrate. Almost all the polyatomic ions are anions. There's only one polyatomic cation that we're going to use in this class, and that is ammonium, NH4+. I guarantee you that's on that list. Okay? It's the only example on quiz problems, on exams. We have no choice but to use ammonium. Okay? So here are two polyatomics together. Again, just read them off. Ammonium nitrate. Anyone know what ammonium nitrate is used for?
It's an oxidizer used for explosives.
It's a fertilizer. We're gonna stick with fertilizer. Okay. What you wanna do in your free time, that's your free time. So this is our crystal lattice again. These are ionic compounds, okay? This is sodium chloride, two monatomic ions, okay? We have our positive sodiums and our negative chlorides. They're just sitting next to each other because positives attract negatives. They just sit next to each other. The calcium carbonate works the exact same way, but instead of having these single chloride ions, you have this big chunky carbonate ion, okay? So the carbonate ion stays a unit. It does not break apart. So you have positive calciums sitting here with all of these negative carbonates, okay? And they arrange again in an ordered arrangement so that their charges cancel and we get this crystal lattice. So behavior, appearance-wise, there's no difference between monatomic ions and polyatomic ions. Here's another thing. This is easy, okay? Don't make it more difficult than it has to be. We can classify compounds as binary, tertiary, and quaternary. All this means is how many different elements are in it, okay? If there are two elements, I don't care if it's ionic, I don't care if it's molecular, I don't care if it's polyatomic ions or what. If there's two different elements, it's binary. If there are three, it's tertiary. If it's quaternary, there are four. Okay? So all you have to do is look at your formula, count how many different elements, binary, tertiary, quaternary. Done. Okay? So if I tell you calcium carbonate, binary, tertiary, quaternary.
Binary.
Why?
Because you got, what was it again?
Calcium carbonate. So calcium carbonate was CaCO3.
And what is three?
There's three.
Yeah.
It's tertiary. Okay? Like I said, we don't care what arrangement they're in. There are three different elements. There's calcium, there's carbon, and there's oxygen. We don't even care how many of each one there are. There are three different elements, so it's tertiary. Okay.
Even if it's, go back one, even if it's in parentheses, it's still
Yeah.
two.
So we'll learn what these parentheses are. What that's do is that's telling us this NH4 is a unit. Okay. So when we're talking about ionic compounds, that's going to be important. But for binary, tertiary, and quaternary, that's not important. We have nitrogen, hydrogen, carbon, and oxygen. That's four. Now we can start talking about our formulas. Okay. You know NaCl, right? But if I told you calcium nitride, what's the formula for that? You would look just like you're looking right now. You have no idea, right? There's a way we can figure it out. Okay. Remember, ionic compounds, they combine the positives and negatives to get a neutral charge. They want to cancel out. Okay? So if I write sodium, what is the charge on sodium? And I write chloride. What's the charge on chloride? -1. How many sodiums do I need to cancel out that chloride? One. How many chlorides do I need to cancel out that sodium? One. So I only need one of each. So I can write NaCl. When I write NaCl, these ones are implied. Okay? You don't write those ones. Okay. If I put Na2, Cl2, is that balanced charge-wise?
Yeah.
Yes, but it's not correct. Okay? Just like fractions, you have to simplify if you can. Okay? You can simplify that from 2 and 2 to 1 and 1. It's the smallest ratio that is balanced. Okay?
So if it's balanced, it's always gonna be one. Well, nothing.
No, there will be times that you'll have other numbers, and that's coming probably next slide. Okay, so here are a bunch of examples. Okay, remember, our positives, so the charge on the positive ion times however many of them you have has to equal the charge on the negative times however many you have. Just like 1 times 1, 1 times positive 1 is positive 1, 1 times negative 1 is negative 1, they combine to 0. Okay. So here's our NaCl again. Here is calcium nitrate. Calcium has a +2 charge. Nitrate has a -1 charge. So it takes 2 of them to cancel out the +2 on the calcium. Okay? So our formula for calcium nitrate is calcium, 1 calcium, 2 nitrates. But we signify that that nitrate is a polyatomic ion. It's a group. It's a unit. It does not break apart by saying we have calcium nitrate. Okay? That means if our 2 is outside of the parentheses, that means we have 2 of everything that's inside the parentheses. Okay? This is not the same thing as saying Ca(N2O6). If I took the 2 times 1, 2 times 6, I would get that. That is not correct. You never want to write something like that. You're saying you have 2 nitrates. Okay? And nitrate is NO3 and nothing other than NO3. Here is sodium sulfate. Sodium has a +1 charge. Sulfate has a -2. So in this case, we need 2 sodiums to balance out the -2 on the sulfate. So we have Na2SO4. And we have Na2SO4. There's 1 sulfate. We don't have to put in parentheses 1 like that. And you don't have to put the parentheses without the 1. If it's a 1, you leave it as is, just like that.
So the parentheses only counts in that.
The
It's not a 1.
Right. The
It's a group.
You're right. Parentheses only come in if it's a number other than 1, and that number is applying to a group of atoms, not a single atom. Okay. The next one is barium chloride. Barium has a +2 charge. Chloride has a -1 charge. So again, we need 2 of the negative chlorides to balance out the +2 barium. Okay? And then more complicated situation is here we have barium that's +2 and phosphate that's -3. If I have 1 phosphate and 1 barium, is that balanced?
No.
No. If I have 2 bariums and 1 phosphate, is that balanced? No. So now what do I do? Okay.
3 bariums, 2.
Right. If you can do that multiplication in your head, that's great. Okay. You can say, well, if I can multiply my 2 by 3 to get to 6, and I can multiply my 3 by 2 to get to 6, and so I would have Ba3PO4 2. Okay. But there's a simpler way to do that. Sort of another one of those little, you can do it even if you don't know what you're doing type things. So I'm going to write barium 2+ and PO4 3-. Okay. In our final compound, what is the subscript on our barium? 3. Where do you see a 3 up here? There's a 3 here, right? What is the subscript on our phosphate up there? 2. Where do you see a 2 up here? On the barium. All we have to do is take the charge on this one and write it as a subscript here. Take the charge on this one, write it as a subscript here. So we get barium 3, phosphate 2. That does the math for us. Okay? Your question?
Yeah, so let me switch you like that. When they're on top of the superscript, they're referring to charge. When we move them down as a subscript, they're referring to
The number that you have.
the number.
So that means we have 3 bariums and 2 phosphates.
Okay.
Okay? You can always do it this way. You can even do that with sodium chloride. That's +1, that's -1, so we get 1 and 1, right? There's our NaCl. Okay? Let's do calcium oxide. We have calcium, oxygen, 2 and 2. So you get Ca2O2. Is that right? No, why?
Because it's not simplified.
It's not simplified.
It's gonna be C.
So if you do this flip method, you have to at the end say, can I simplify this? Okay? With our barium phosphate, we can't simplify that, right? 3 and 2 cannot be divided by the same number and give us whole numbers. Okay? These numbers, these subscripts always have to be whole numbers. So remember, take charges, flip them, make them subscript on the other ones.
So it would be just CAO.
It would be CAO, yep. So you, this 2 simplifies, simplified to 1s, and you don't write 1s. So it's CAO.
What if it was 4s?
What was 4s? What if you had,
It'd still be 1, right? Was
Would it still just be CAO? And then CA4
there's a, this wouldn't exist, but, so don't throw me in chemistry prison. If you had Ca4O4, it still simplifies to 1s,
Okay,
so it becomes CAO.
okay.
So what is the formula for calcium nitride? What is the charge on the calcium in this? So I'm gonna write calcium +2, right? Nitride. Nitride is dealing with nitrogen. It's not one of those polyatomics. Okay, it's a monatomic. So what's the charge on nitride? Right. 3 minus. -3. Okay? So what is the formula? What are my subscripts that go on my calcium nitride? Ca3 and 2. 3 went there, 2 went there. Okay? So if I was going to write this out, rather than thinking like individually, the way I would do it, I would say calcium, it's calcium. What's my subscript? What's the charge on nitrogen? So I would say the charge is 3. Then I would say nitrogen, what's the charge on calcium? 2. And that's how I would do it. If you want to write them out and swap them, be my guest. The more you do it, then you'll move on to my method. Okay. Because I can just in my head say, what's the charge on nitrogen 3? What's the charge on calcium 2? Okay. What's the formula for barium nitrate? Here is, where's he? Right there. Where barium goes?
6.
Oh,
Alkaline, or
left, right?
left, alkaline middles,
Bottom.
period 6.
Ah, there. Wow, way down there. Okay. So there's barium. Barium nitrate. You haven't had a chance to memorize the polyatomic ions yet. So nitrate is NO3 minus. Okay? So what's the formula for barium nitrate?
BA.
Parentheses, NO3.
We get 2 from. With the 2, why isn't it beside the BA?
So when we put, what's the charge on the barium ion?
2 plus.
2 plus, and then we have nitrate minus. So the this 1 went to the barium, 2 went to the nitrate.
Oh, so you already just.
Yeah.
Okay.
So here's our 1 that was here, if we don't write it.
Yeah.
And then, because we put a subscript on polyatomic ion, we have to put parentheses. And then there were 2, because that 2 was there. Potassium sulfate. Sulfate is SO4 2 minus. So what's the formula for potassium sulfate? So I heard K, okay, let's do that. K plus. So I have K, SO4 is my sort of my starting point.
So K2.
K2 SO4.
Yeah.
Done. There's one SO4, because of 1, but because it's 1, there's no parentheses. The 2 came from there. Over,
Explain why there's no parentheses again? Sorry.
yes. You have K2 SO4. The subscript on the SO4 came from the charge on potassium. What was the charge on potassium? 1. So what you really have here is that.
But that's not right.
Oh, but you don't have to write it
So
out
you,
like that.
if there's a 1, you don't have to write the parentheses or the 1.
But if it was like 2 or something like that, you'd write the parentheses.
Right, so if you had aluminum sulfate, 2 from the sulfate goes there. Aluminum forms a what charge? It's number 13. 3.
So,
So the 3 comes here. So then we have to put parentheses. Al2SO4 3.
Okay.
are we finding the charge from the periodic table?
Yes.
How do you do that?
These form plus 1s, plus 2s, plus 3s. It's how many valence electrons it has to gain or lose to get to 8. Okay. So this one loses 1, 2, 3. So it's plus 1, plus 2, plus 3. These lose 1, lose 2, lose 3. So it's minus 1, minus 2, minus 3. And then this 4 is kind of in purgatory there, that we don't really deal with. Okay. So here's ammonium phosphate. Does anyone remember the formula for the ammonium ion?
Is there like a chart for that?
NH4 plus. Okay? And what's phosphate? PO4 3 minus. So, that's my formula. NH4 parentheses 3 PO4. Okay. 3, you now have to take Now, 3 of these, because the charge was 3 was here, our 1 came down here, the 1 we don't write it. Got it? Last one, I think. Lithium nitrate. Charge on lithium? Plus?
+2.
No, it's a 1. It's in the first column, first
Okay,
group,
so it'd be
so it's a +1. And nitrate is NO3 what? Minus. So what's my formula?
So it would be NO3.
3. LiNO3. That NO3 is a unit. You're never going to have anything other than NO3. You can have multiple NO3s, but you can't have this part of it. Okay. Remember, just like I just said, polyatomic ion does not break apart no matter what you do. That sulfate is going to stay SO4, okay? For the rest of our lives, it's going to stay SO4. If you put potassium sulfate in the water, it's ionic, which means it's an electrolyte, which means it's going to dissolve in water and break apart into its ions, okay? That means you get potassium ions and sulfate ions, okay? And the number of ions that you get out of that are exactly equal to the subscripts on them, okay? So we get 2, that's not right. We get 2 potassium ions, okay? 1 sulfate.
They put the 2 in the wrong spot.
Yeah, 2 is in the wrong place. Fix it on your slides so you don't confuse yourself later. That should be K2 SO4 goes to 2K plus SO4 2 minus. Okay, with the little state symbols. Solid. So here, with our sodium chloride, remember there's 1s here that are implied, so we get 1 sodium and 1 chloride. Okay. How many of each ion would we get out of this?
One.
What ions are in here? These are polyatomics, right? Yes. The ammoniums stay ammoniums, so we get 3 of them. The phosphate stays phosphate, and we get 1 of them. Okay? If we had calcium chloride, how many of what do we get?
1 calcium.
Yeah.
1 calcium, 2 chlorides. Okay. What about calcium nitrate?
1 calcium.
Right. 1 calcium, 2 nitrates. If you put a molecular compound in the water, it doesn't break apart. So, if you put 1 sugar molecule in the water, how many things do you have floating around? 1. Doesn't break apart. So 1 stays 1. So I don't know why. I did that. So what is the name of this compound? Aluminum oxide. The metal, you just say the name of the element, aluminum. The anion, you say what element is it. Oxygen, change it from oxygen to oxide. You don't have to do anything about the numbers. Those numbers are wrapped up in the name. Because if I told you what's the formula for aluminum oxide, you should be able to figure that out without being told that, right? So if you're told aluminum oxide, you know that. Yeah? What's the name of that?
Sodium.
Sodium
Chloride, how about that one?
Sodium
Nitrate.
Nitrite. You're just waiting for me to finish your sentence. Because it could have been sodium nitride. NO2 is nitrite. Okay? That's sodium nitrite. What's the name of that?
Magnesium chloride.
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 Duh.
It's an element. It's not a polyatomic ion. So you just figure out the name of the element, chlorine, and end it with "ide." Magnesium chloride. Okay? Just like sodium chloride. We have magnesium chloride. What's the name of that one?
Magnesium nitrate.
8. NO3 is the nitrate. That's magnesium nitrate. How about that one?
Barium oxygen.
Barium oxide. It's an element, so you just end it with "ide."
Okay.
How about that one? Lithium nitride. Yep. It's an element. The element nitrogen, so it's "ide."
Okay.
Yeah.
So it's a single element, it's an I, and if it's a compound, you have to know it.
Yeah.
The
Yep.
numbers, the ones.
So if the anion is an element, end it with "ide." If it's a polyatomic ion, just say the name of it. Yeah.
And then, this is all gonna be implemented, like, I should have them all memorized by this for next week.
The polyatomic ions?
Yeah.
Yes.
That's not fun.
I thought you said this was gonna be easy.
Yeah.
What was going to be easier? What?
No, this is.
There are only like 6 or 7 of them. And if you remember the 8s,
even remember.
if you remember the 8s, you automatically remember the ites. Here's a flow chart determining if there's a polyatomic for naming ionic compounds. Okay? Just like we said. For the metal, say the metal name. Say the element name. For the anion, if it's an element, end it with "ide." If it's a polyatomic ion, say the name of it. Nitrate versus nitride. Okay. Now we get to these messy transition metals. Because if yeah.
I wasn't raising my hand.
Oh, okay.
Sorry.
Okay. So before, if I said, what's the charge on a calcium ion, or what is the formula for calcium nitrate, you can tell me. Because nitrate is always -1, calcium is always +2. If I ask you, what's the formula for iron nitrate, you can't tell me, okay? Because I didn't give you enough information. Iron could be +3 or +4. We'll see. Okay. Here is copper. This is copper oxide, and that's copper oxide, right? But they're very different. Okay. So, looking at this, what was the charge of the copper here?
+1.
+2. Why 2? You're at. Remember, they have to balance, right? And so our subscripts are 1 and 1, which means the charges on them have to be equal. And we know the oxygen was -2, so the copper had to have been +2, right? What was the charge on the copper here? Just 1, because it took 2 of them to equal the -2 on the oxygen, okay? So if I give you this, you can now figure out what the charge was. These are the most common elements that form multiple charges, okay? You don't have to memorize these. Just know that there are, it's fair game for me to give you a formula with the iron 2 or the iron 3 and have you figure it out. Okay? You don't have to memorize that iron is 2 and 3. But keep in mind that if I give you a formula, the iron could be one or the other. Okay. So, iron can be 2 or 3, copper can be 1 or 2, tin is almost always plus 2. Okay. Really the ones you're going to run across the most in here that have multiple charges are iron and copper. Okay. Because we use iron and copper in lab. Okay. And iron and copper are very common. Iron and copper are everywhere, right? So, if I gave you, said, what is the formula for iron 2 nitrate? That iron 2, that 2 applies, that tells you the charge of it. It's iron 2 as opposed to iron 3. So if I'm telling you have iron 2 nitrate, what is the charge of my iron? 2 plus. 2 plus, and then I have nitrate, and it's the same exact as we were just doing. Okay? If I say it's iron 3, that's the only change you have to make. Okay? And then when you swap them, your subscript on your nitrate changes. Okay? Same thing with the copper. So you can go this direction from name to formula, or you can go the other way. And we already did that, right? That's what we did here. We went from formula to name. We figured out the charge. We said here the charge was 2. So what is the name of that compound? Yes. It's copper 2 oxide. And what is the name of that compound? Copper 1 oxide. The copper oxide is the easy part, but you have to then think, I have to specify what the charge on that copper is. And we figured that out based on knowing the charges had to be balanced. So here, plus 2 balances minus 2, so it's copper 2. Here it took 2, which means that had to have been plus 1 there. Here are some common ones. Don't worry too much about that slide. You may, in a homework or something, run across cobalt or mercury, but I think it should be very obvious when you get it. If it tells you, if all of a sudden it says cobalt 2, that should ring bells and say cobalt could be something else, but it's telling me it's 2. The name of that, Mn is manganese.
Manganese oxide.
Manganese what?
2.
Manganese 2. Charge on that.
Manganese 4.
Manganese 4 oxide. We're right here. This is a little more complicated than the other ones we did, right? It's here that the charge went over here. So we know oxygen is minus 2, and there's 2 of them now. So what's our total negative charge? Minus 4. And we have to cancel that out with just 1 manganese. So what does that manganese have to be? 4. It has to be plus 4. So it's manganese 4 oxide. What's the name of this?
Copper 4.
What's the charge on sulfate? Anybody remember? 2 minus. So sulfate is 2 minus. What's the charge? What's the name of that compound? Copper 2. Because it only takes 1 copper to balance it out. Chromium can have multiple charges. What's the name of that? Chromium 6 oxide. Remember, again, we have oxygen is minus 2, and there are 3 of them. So we have a total of minus 6 and we have to cancel it with 1 chromium. So that chromium has to be +6. And last thing before break, what is the name of that? Iron 3 nitrate, right? Because that 3 came from there. We have a total of -3 here. You have to have +3 on the iron. Okay. So let's take a break. If you want to turn your homework in, you turn it in up here.